Yes, good afternoon to all. Myself, Dr. R. Subbarao, Professor of Mathematics, Department of Engineering, Mathematics and Humanities, SRK Engineering College. See, already we studied 2 units in our classes. The third unit is related to curve fitting and estimation theory. Curve fitting already you had studied in your earlier classes. So what is curve fitting and what are the different types of curves that you are going to fit and what not other concepts that you are already discussed. And in the third unit, the second part is estimation theory. In the estimation theory, we will study about point estimation, criteria of good estimation, unbiasedness, consistency, and of course sufficiency and efficiency is also there. Interval estimation, methods of estimation, maximal likelihood estimation, and again sufficient statistic, concept and examples, complete sufficiency, and their applications. See, the concept of estimation will comes under statistical inference. What is statistical inference? What are its different parts in it? See, for any decision making, we are supposed to estimate and then you are going for the testing of hypothesis. Therefore, we are trying to give some conclusions on the population parameters or any statistical hypothesis. For this, there are 2 major parts are there. One is estimation theory and the other is testing of hypothesis. Therefore, the statistical inference has 2 arms. One arm is the estimation theory and the other is the testing of hypothesis. So in the estimation theory, we are trying to estimate the population parameters using different methods of estimation and all other things. In testing of hypothesis, what are all the estimated things are there or estimated parametric values are there, they will be tested in testing of hypothesis. Therefore, for giving conclusions on the statistical hypothesis or else on statistical assertions, we try to go for these 2 parts. One is estimation theory and the other is the testing of hypothesis. See, statistical inference is the process of drawing conclusions from the data subject to some variations. Because if I ask any one of you how many marks you will get in your coming examination, you will assess based on your prejudice. One may say that I will get 20 out of 30, another may say 25 out of 30, and whatever it is. No doubt that you may observe some sort of variation, what your exact mark and your estimated mark. So that variation is common, that what you are calling as a random variation. And more substantially, the term statistical inference, statistical induction, and inferential statistics are used to describe systems of procedures that can be used to draw conclusions from the data sets arising from systems affected by random variation. Of course, such as observational errors, random sampling, or random experimentation. Okay. Here, the outcome of statistical inference, your maybe answer to the questions, what should be done next? Where this might be decision about making further experiments or surveys, about drawing a conclusion before implementing some organizational or governmental policy. And of course, any statistical inference requires some assumptions. Those assumptions are regarding the statistical model, and of course, it is a set of assumptions concerning the generation of the observed data and the similar data. Observed data differs with the similar data. And descriptions of statistical models and descriptive statistics are typically used as a preliminary step before more formal inferences are drawn. And the statistician distinguish between 3 levels of modeling assumptions. One is fully parametric or parametric. Second one is non-parametric. And the third one is semi-parametric. That means you can see that three types of estimations or three types of models. One is parametric models, and the other is non-parametric, and the other is semi-parametric. And of course, in fully parametric, the probability distribution describing the data generation process are assumed to be follow some probability distribution, and we are trying to estimate those population parameters, and then we will go for the testing of hypothesis. The most general parametric estimations are the probability models that we consider are normal population, binomial population, and Poisson population, exponential population, and whatnot. These are widely used experimentations. And non-parametric are the assumptions made about the process generating the data are much less than in parametric statistics or maybe minimal. Here, you should not estimate or you should not take any basic assumptions of the populations. It is purely depending upon the data sets that you are considering. See, another case is the semi-parametric. The term typically implies the assumptions between fully and non-parametric approaches. See here, one may assume that the population description may have a finite mean. Furthermore, one may assume that the mean response level in the population depends in truly linear manner on some covariate, but not make any parametric assumptions describing the variance around that mean. And of course, generally, the semi-parametric models can often be separated into structural and random variations. The well-known Cox model is a set of semi-parametric assumptions. We have several models are there. Cox model is one of the model, and this Cox model is one of the example for the semi-parametric assumptions. In statistics, estimation refers to the process by which one makes inferences about a population based on information obtained from the sample. Because the estimation theory is you are trying to estimate the population parameters on the basis of some samples that are considered from this population. Therefore, the estimation refers to the process by which one makes inferences about the population. But means you are giving inference regarding the population, but you are not studying the entire population. You are giving population parameter estimations basing on the some information that is available with you with the sample. See, the statistical inference may be classified into two parts, as I told you, the theory of estimation and testing of hypothesis. Now we are trying to concentrate more on the estimation theory. So the theory of estimation, you are trying to say that an estimator, that means you are supposed to estimate your population parameter using some sample observations. The set of observation that what you are calling is estimator. So that estimator may have some characteristics. That estimator may be good, but estimator may not be a good estimator. That depends on the samples that you are assuming from the population. If you are truly generated samples that you are considered from the population, your estimation is a good estimation. Sometimes there are some unrelated sample observations maybe also be possessed in the population. You should not consider those sample observations. Generally, you are calling an estimator is a good estimator provided it satisfies some conditions. So a good estimate is also very much close to the population parameter value or true value of the population parameter. Whenever or which estimator is very much close to the population parameter, that estimator is called a good estimator. So a good estimator will consist of some characteristics. I'm saying that Rama is a good boy. So what do you mean by good? I would like to define that or say that what are the characteristics of that good. So he will regularly attend to the class. He has very less absentees, and he will attempt the questions whatever the poses by the teacher, and whatever the assignment is given, he will write it properly. Like that, I will assess or characterize a student. In the similar way, I can also define some characteristics for the good estimator also. So an estimator is said to be a good estimator, provided it is satisfying some conditions. What are those conditions? Unbiasedness, consistency, sufficiency, and efficiency. So whatever the estimator Tn, I am considering that it should contain these four characteristics. I'm using the word Tn. What do you mean by Tn? A set of n observations which are proposed to estimate the population parameter is called an estimator. So that Tn, that is statistic Tn. Okay. Now that statistic should contain all these four parameters. So I define this one by one very clearly. What is unbiased, what is consistency, and whatnot. Let us try to assume first what is an unbiased estimator and what is an unbiasedness. A statistic Tn, and of course, in some cases you may write small t or capital T. It doesn't bother, but of course, small t is better. So Tn is equal to T of x1, x2, and so on xn is said to be an unbiased estimator of the population parameter theta if expectation of the statistic Tn is equal to the parametric value. That means expectation of the statistic is equal to parameter. Then I can say that this is a good estimator. That is a unbiased estimator. Okay. See, expectation of Tn is equal to theta. But the expected value of the sample statistic is equal to the true parameter value. That's what I am calling as the unbiasedness. And of course, if expectation of Tn is not equal to theta, then I will call it as a biased estimator. So biasedness is of two types, positively biased and negatively biased. When I can say the estimator Tn is positively biased, if the expected value of the statistic, that is Tn, is greater than theta, then this Tn is positively biased of the parameter theta. If expectation of Tn is less than theta, then this Tn is said to be negatively biased. That means positive side, negative side. Basing on that, I'm defining this. So this is what I'm calling as a unbiasedness or unbiased estimator, I can say. And this Tn, if expectation of Tn is equal to theta, then this Tn is called an unbiased estimator of the population parameter theta. See, simply I'm writing here E of Tn is equal to theta. What is the Tn? That is a sample statistic Tn. That means a set of sample observation which is proposed to estimate the population parameter theta. If the expected value of that Tn is equal to theta, I'm calling this as unbiased estimator. If expectation of Tn is equal to true parameter theta, unbiased. If expectation of true parameter, expectation of the statistic is not equal to the parameter, then it is called biased. So positively biased, negatively biased. If expectation of T is greater than theta, it is positive, and expectation of T is less than theta, it is negatively biased. Next I will go for the consistency. See, generally speaking, consistency means it is convergence in probability. Convergence in probability. Consistency means convergence in probability. We know what is the definition of convergence. I'm not going to discuss it. The definition for consistency is an estimator Tn, T of x1, x2, and so on xn, based on the random sample of size n, is said to be consistent estimator of theta if Tn converges to Tn converges to theta, if Tn converges to theta under probability, that is n expectation of Tn converges to theta under probability when n tends to infinity. In other words, Tn is a consistent estimator of theta if for every epsilon greater than 0, there exists some eta greater than 0, a positive integer, and of course n greater than or equal to m, such that probability of modulus of Tn minus theta is less than epsilon tends to 1 as n tends to infinity. And also you can write it as probability of modulus of Tn minus theta is less than epsilon greater than 1 minus eta for all n greater than or equal to m. So this is more or less a definition of the convergence. So simply speaking, consistency means convergence in probability. The symbol for writing the convergence in probability is write P on write P on the arrow, that is P, and where n you are taking n is large values, that is n tends to infinity. So expectation of Tn converges to theta under probability for large values of n, then that estimator Tn is said to be a consistent estimator. And the third case is efficiency. See, efficiency is nothing but the reciprocal value of the variance of the sampling distribution of the statistic is nothing but the efficiency. And efficiency is denoted with E. Efficiency is denoted with the E. So we can define it as the reciprocal of variance of the sampling distribution of the statistic is nothing but the efficiency. And your efficiency E is equal to 1 by variance of T. For example, there are two consistent estimators, T1, T2, and variance of T1 is less than variance of T2, then the efficiency of T1 over T2 is nothing but E is equal to variance of T1 by variance of T2. I repeat, suppose you have two consistent estimates. That means if at all it is efficiency, means they should be consistent. The efficient estimator is always consistent. So T1 and T2 are two consistent estimators, and variance of T1 is less than variance of T2. Efficiency T1 over T2, that you are defining as T1 over T2, E is equal to variance of T1 by variance of T2. That's what you are defining as efficiency. And the last property of the criteria of good estimator is sufficiency. An estimator is said to be sufficient for a parameter if it is consists of all information in the sample regarding the parameter, which means that the estimator that what you are considering should have all the information regarding the parameter theta. That means if you are taking any other estimator, it does not have more than this information. Okay. So in other words, the conditional distribution of the sample observation given statistic is independent of theta. That is probability of x1, x2, and so on, xn given t is equal to independent of theta. Then the statistic t is sufficient for the parameter theta. So sufficiency is nothing but a concept of information. So an estimator is said to be a sufficient estimator if that estimator is containing all the information regarding the population parameter theta. If you are taking any two estimators, or if you are taking any two estimators, T1 and T2, then the T1 is sufficient. T1 has all the information when compared with the T2 also. So that's what you are defining as a sufficiency. So this part, the concept, that part you learned so far are nothing but the criteria of good estimator. That means you are saying that an estimator is a good estimator. So an estimator is said to be a good estimator means it should satisfy all these four conditions. Okay, you have defined what is an estimator. So an estimator is defined. Now my question is, what are the different types of estimates? There are two types of estimates are there. One is point estimate and the other is interval estimate. So the types of estimates are two types. One is point estimate and the other is interval estimate. You should be very clearly distinguish these two. Point, that means single one point you are giving. Interval, you are giving more than 1 point. So interval estimation and point estimation are the two types for the population parameter. A statistic is characteristic. A statistic is a characteristic of a sample. Generally, a statistician is used to estimate the value of the population parameter. Okay. So before you go for the real statistic, you should real definition of point and interval estimation. You should go for what is a parameter. A parameter is nothing but a measurable characteristic of a population. So a parameter is in another way, you can define this parameter also the statistical constants of a population. What do you mean by statistical constants? The statistical constants are nothing but the measures of central tendency and measures of dispersion. You know what are the different measures in measures of central tendency? Mean, median, mode, geometric mean, harmonic mean. Similarly, you know what are the measures in dispersion also. The measures in dispersion are range, quartile deviation, mean deviation, and standard deviation. So if you are calculating these values or these measures for a population, you can call it as a parameter. A parameter. Similarly, you can call it as a statistic is another definition. Is there. If you are calculating the statistical constants for a sampling distribution, that what you are calling as a statistic. What do you mean by sampling distribution? A sampling distribution is nothing but it is a frequency distribution obtained from the different samples that are generated from the population of size which is defined as n. For example, let us try to assume that there are n number of observations are there in a population. That is capital N number of observations are there in a population. I would like to select a sample of small n. I would like to select a sample of small n. And of course, this may be a with replacement and without replacement are there. I don't consider about the with replacement without replacement concept for this at this juncture. So how many different samples that I can generate from the population? Let us say that there are k number of samples are there. That is capital N is the population size, small n is the sample size. Then I can generate NCN number of sample observations from that. So NCN is equal to, let us assume that is k. That means I can generate k number of sample observations from the population. Okay. For these k number of sample observations, for this k, I can calculate different different measures. For example, I would like to find mean. There are k samples are there. For these k samples, I can find the mean also. Write all those means. Let us try to prepare a frequency distribution for all these means. I will get a frequency distribution. That frequency distribution is called a sampling distribution of means. Why? Because for all these samples, I'm finding the mean and then I'm preparing a distribution. Therefore, it is called sampling distribution of means. For example, if I was calculate a standard deviation for all these samples, then I will get a frequency distribution with all these standard deviations. That sampling distribution is called sampling distribution of standard deviations. Like that, for each measure you can calculate. Okay, now let us try to see that what is a point estimate and what is a interval estimation. So the population parameters can be estimated with only these two ways only. And of course, there are some estimates, Bayesian estimation is also there and some other estimation also there. As far as our syllabus is concerned, we are interested to go for up to the point estimation. What is a point estimation? A point estimate of a population parameter is a single value of a statistic. I told you an example also. What is how many marks that you will get in the coming examination? One student may said that 20. That means he is giving a single value of the population parameter. That means how many marks you will get in the examination. That's what I'm calling as a point estimation. A point estimation is nothing but simply giving a single estimated value to the population parameter basing on the statistic under consideration. That's what I'm calling as point estimation. For example, the sample mean x bar. Here there is a small mistake is there, x bar. The sample mean x bar is a point estimate of the population mean mu. You know that the mu is the mean of the normal population. Sigma is the variance standard deviation of the normal population. P is the population proportion. Similarly, the sample proportion small p is a point estimate of the population proportion capital P. So that's about what is a point estimation. Now let us go for what is an interval estimation. An interval estimate is defined by two numbers between which a population parameter is said to lie. For example, I ask you how many marks you will get. One student may say that I will get in between 20 and 25. I will get nearly 20 and 25, in between 20 and 25. That means that student is assessing that his coming mark will be lies between 20 and 25. So the lower limit is 20 and the upper limit is 25. So basing on that, some confidence is also there. That means probability of that A less than X less than B is equal to some confidence 1 minus alpha. For example, A less than X less than B is an interval estimate of population mean mu. It indicates that the population mean is greater than A but less than B. So you will go for the confidence interval. What do you mean by a confidence interval? The statisticians use confidence intervals to express the precision and uncertainty associated with the particular sampling method. For example, I'm telling you how many marks you will get, that you are saying that you have some confidence that you will get it. You have some probability value you will get it. You have some assumptions. What is the question paper it is, and how I attempted for the examination, and how the value will be. Basing on that, you're trying to give some conclusion. That means you have some confidence that I will get in this much of marks. So a confidence interval consists of three parts. One is a confidence level, and there is a statistic, and there is a marginal error. This marginal error is always common. So whatever you think, it will not be happen. Okay. Next, the confidence level describes the uncertainty of a sampling method. The statistic and the margin of error define an interval estimate that describes the precision of the method. See, the interval estimate of a confidence interval is defined by the sample statistic plus or minus margin error. Plus or minus marginal error. For example, suppose that we compute an interval estimate of a population parameter, we might describe this interval estimate as a 95% confidence interval, which means that the sample statistic plus or minus marginal error into 95% of the time. That means you're trying to take an error with a confidence of 95%. Okay, so the confidence intervals are preferred to be the confidence intervals are preferred to point estimates because confidence intervals indicate the precision of the estimate and the uncertainty of the estimate. Okay, so next is confidence level. Confidence level or level of significance, or these are some other points that you can observe. 95% confidence coefficient is nothing but 5% level of significance. 5% level of significance. Like that, you can define confidence level also. See, how to interpret the confidence level? You have collected all possible samples from a given population and computed confidence interval for each sample. Some confidence interval would include the true population parameter, others would not. A 95% confidence level means 95% of the intervals containing the true population parameter. Similarly for 90% also. Okay, so the interval estimate, finally you can define like this. Estimating the population parameter using two statistics T1 and T2 such that probability of T1 less than theta less than T2 is equal to 1 minus alpha. Then estimation, the interval estimation where T1 and T2 are called the confidence limits or fiducial limits. You can call this T1 and T2 as confidence limits. The interval T1 comma, you should write them in an interval which is within the brackets T1 and T2. That's what you're calling as a confidence interval. And 1 minus alpha is called confidence coefficient. 1 minus alpha is called confidence coefficient. Therefore, the 1 minus alpha confidence interval of the unknown parameter theta is nothing but probability of T minus Z alpha into standard of T less than theta, that is less than T plus, here there is a small mistake, is that this is T plus. T plus Z alpha into standard of T, which is equal to 1 minus alpha. You can generate 95% confidence intervals and 1%, 99% confidence intervals also. So the 95% confidence intervals are like this. Probability of X bar for a mean, so the parameter mean mu, if you are defining probability of X bar minus 1.96 into sigma by root 10 less than mu, that is less than X bar plus 1.96 into sigma by root 10, which is equal to 0.95. Similarly, for 99%, probability of P minus for population parameter P, that means proportional matrix, that you are taking proportion. P minus Z of 1% 2.58, that is confidence, the table value is 2.58 are critical values. P minus 2.58 the root of P Q by N less than P plus 2.58 to root of P Q by N, which is nothing but 0.99. So these are called the interval estimations for a population parameter mean mu and the population proportion capital P. So this is the concept of point estimation and interval estimation. So this is the process of estimation will go on this process. In today's class, we had learned about what is a statistical inference, what is a point estimation, what is an interval estimation, Besides that, what is the criteria of good estimation? Okay. In the next class, we'll go for how to estimate the population parameters using confidence intervals. Thank you. Thank you, Varun.